questions that were posted on the website, so I stole those, but also added a couple. One was, is there some massive unobserved gas phase? That is, do galaxies have some source of gas that fills in the baryons we don't see, although maybe we see all the baryons as of this morning? Another question was, do early type quiescent galaxies grow new disks? If so, what is the timescale for this growth? This came out of the discussions we actually had on Monday, that Jay and I were arguing about disks in galaxies. How does cold gas remain around galaxies but not contribute to the star formation? I think we've talked a little bit about that, but some of it does. And finally, the last question, which grew out of this morning's argument, in the CGM, can we ever model the CGM correctly, or have we done so already? Shall I take a vote? Who wants to talk about the CGM?
What does correctly mean?
Yeah, well, that's the question. There is a question here about what correctly means. I have one person who wants, two people who want to talk about the CGM. Three.
What was the question, sorry?
The question is, we're voting on whether we want to talk about the CGM or we want to talk about all these other points. So the CGM was very exciting this morning, so I wanted to see if people want to keep talking about the CGM. I'd like a pleasant discussion rather than shouting. Or do we want...
Let's do the other things.
Let's do the other things first, okay.
Yeah.
So let's ask the question, is there some massive unobserved gas phase in the galaxies? Does anybody believe that there can be such a thing? Jay?
It's called the outer disk.
So how big is the outer disk?
Not only how big is it, but what fraction of the H1 might be optically thick, what fraction is molecular, and what fraction is ionized. How big are disks really? It's not a giant massive thing, but it's significant, and it can have a significant, like the jolt, and a significant cross-section in ionized gas.
Okay, Joel, do you want to say something about this?
Well, actually, I wanted to raise something else about the extent of gas. So I think Tim was talking about this, but there's some work by, well, the first author is Tom Oosterloo, where they looked at early type galaxies and saw really very large, some large disks around early type galaxies, not, well beyond the optical image. And I thought that was, kind of surprising. And so, when you look through the lines of sight, sometimes you're going to be looking through a disk.
Well, so this actually brings back the CGM point. How often, we know from what Jessica showed earlier that there's not much difference between the star-forming and quiescent galaxies. If you can imagine that has some relationship between early type galaxies and late type galaxies morphologically, which isn't strictly true as we saw earlier, but if there's a rough correlation there, how many of these large disks are we actually putting sight lines through? Is that part of this question, or is this?
How far out are these disks going?
Yeah. Well, they go out to.
Estimation.
They certainly go out to. Yes.
Yeah.
Absolutely. I'm actually a co-author on this Oosterloo paper that Joel is mentioning, because I was actually part of the survey. So.
All of the rest of your dense systems that extend out of the planes, you could say, but I don't think there's that much mass.
But the column densities of the Oosterloo galaxies never exceed 10 to the 20 or so in H1, right? So they are not dense systems in column density. They have a fair amount of mass because they're very big. Right? So they have 10 to the 10th solar mass. I mean, we were observing galaxies which were typically, 10 to the 9th, 10 to the 10th solar masses, but they were in these disks that were up to 100 kiloparsecs across.
That's in H1 and 21 centimeters.
In 21 centimeters, yeah.
So then you're actually averaging the column density over your beam size, which is not small.
Yeah.
Right? And there's also this self-absorption thing, which I don't know much about.
No, not at these columns.
Not at those columns. Yeah.
Well,
not at 10 to the 20.
Small scale structure. It depends on what the power spectrum is. Now take your beam and consider the power spectrum of column densities on the small scale,
yeah, so
then it actually depends what this power spectrum is, etc.
Our resolution was certainly not significantly sub-kiloparsec scale.
Right, so it's very dangerous to talk about kiloparsec average column density and compare them with column densities you get along the line of sight, which get the size of whatever.
So do you think these things are smooth, or are they clumpy?
Yeah, but people
they're dynamically quite
using UV sightlines,
stable and cold.
So it's not very different.
What fraction?
It's different than 20%.
What fraction was this? Well, it's the 40% number that Tim showed earlier. And of that 40%, more than half, so it's like 20% of early type galaxies, have normal rotating big disks. So, okay, so, well, maybe there is mass
Do
hiding.
any, I mean, just,
in
does
those.
any simulation
But-
show those?
There's nothing normal about 100 kilopascal bit.
Does anybody simulate those? Does it?
Or it must be rare, very rare.
So yeah, we do. In fact, Tim
Not
Tim
that-
knows
that
this.
large. Typically, they're about 2.5 times larger than the stereo discs, whatever this number.
Well, those are the H1 disks that you see with an exponential scale length, but when they looked at, these early type galaxies, they got the wrong answer. They found these really big disks.
I mean, Tim could. I'm actually going to hand this over to Tim because he's actually done some of the simulations. So
So I just wanted to say that there's a paper, I can't remember if it's out already or it's coming out very soon, where Paulo Serra takes the atmospheric DH1 observations, compares them directly with simulations from Thorsten Nabb.
it's on Astro PH.
It's on Astro-PH, okay, good. So you can go check that out. They do see these big sort of disks. The details are not exactly well matched. It depends on your feedback process you include in your simulations, but you certainly can get these big H1 disks around early type galaxies in realistic and simulations. If you
Yeah, I mean,
Those are usually signatures of full accretion.
well, these ones match in their sort of kinematics and various other things, but I refer you to the paper for the full details of exactly what they did.
But there didn't seem to be a lot of mass in those disks, the ones that you showed, right? I mean, the origin of the question was, is this a big contribution to the mass budget?
Well, some of them have 10 to the 10 solar masses, so they are significant. I mean, they can be as big as the galaxy mass. That's
Right, but that's still negligible compared to FB times M halo, which is what we're talking about.
yeah. So I do. I mean, yeah. I mean, my personal feeling is that these things exist, but they're relatively relatively rare. Not for elliptical galaxies, but they're relatively rare integrated over all galaxies at some level. And that the amount of mass they contain is relatively small compared to FB times M halo. So I'm not convinced that they're a big source of hiding baryons, personally, but I am interested to see that the simulations are coming. I knew about Paulo's simulations. He was my PhD student, so I knew that they were there. The older simulations of merger simulations actually show that you can only form these disks by having very peculiar merger geometries. But I don't know about the new, I haven't seen the results of that paper. I know it's on Astro PH, I just haven't read it yet. So,
And then how consistent are those with the absorption measurements? Like,
yeah, so that's a good question.
I mean, you could in some of the sightlines, conceivably, I guess, be going through some 70 kiloparsec disk. But I mean, you don't ever see that column. Well, you sometimes see 10 to the 19 in H1. So maybe in those cases, in a few handful of those cases, you are.
And we have a
When you
probe.
a sample of 44 L-star galaxies, I mean, how many of those are going to have these 100 kiloparsec disks?
Yeah, not terribly many, to be honest. And the truth is that we haven't, on the other hand, we haven't probed, in these sorts of galaxies, we haven't probed much below 10 to the 20th. Because the column density restrictions of doing the observations are so, maybe when we get something like the focal plane arrays going on the various telescopes, or when we have SKA phase 1, we can conceivably do quite a bit better. But we haven't gotten there yet, so.
Well, very few of them will have 100 capacities, but almost all of them will have 30 capacities.
Yeah.
Sure.
So. I mean, can you see 30 kiloparsec disks, or is that too close?
Well, each one's the less, right? So we go down to 10 to the 17 or lower in column, right?
And we just, we can't.
We can detect
Right,
the
so-
mean density of the universe if you want. So we can definitely detect these big chunky disks. I mean, the point is, they just end up as one data point on a plot of 100 data points,
That
where
was the
there's this
question.
one weird system that's got a large disk. I mean, it kind of comes down to what do you classify as the CGM.
The CGM would be all of these things, I guess, yeah.
So maybe we need to be more careful about the word CGM at this point. Right? I mean,
Observationally, it's sort of like, I think the question is, observationally, it's a relatively well-defined thing, right? I mean, there are some issues that I think Joel brought up, right? If the absorber sizes are very long and they're cosmological, then, one can make some mistakes in their interpretation. But, let's just say 30 to 300 kpc, that's for 250 kpc.
Okay.
But in terms of the H1, you see these very large H1 disks in 10 to 20% of galaxies. She sees large H1 absorption in 10-15% of the systems. It seems, you know, ballpark about the same.
But it's not, the things that are long in Jessica's analysis are by no means high column density, very neutral.
No, but there are.
It's not, it's a very diffuse phase.
If you just look at the damp H1 absorption profiles, there are, you know, a handful that, and there are 4 that are 10 to the 19 or above.
And those are those that are really
Those ones
close to the galaxies, right?
And
Those
the
are the DLAs.
current sizes are always very small.
And actually, those have the smallest ionization correction, so that the gas there is.
Yeah, but those could be disks.
Those could be disks,
And
those
they
could be,
these
yeah, I mean, if you look at the Milky Way, you know, you see it go all the way to the Lyman system as you go out, all the way down to 10 to 17. So I think that's a fair point.
So, a question that I wanted to know the answer to, maybe Tim started to answer this question, was if we have these big disks, even if they're only 30 kiloparsecs, why are they just sitting there doing nothing? Or are these the things that we think are rejuvenating disks around early type galaxies that are later going to become big bulged SAs?
Why do you expect them to do anything? They have to be unstable to do anything.
Yeah, so
Column is about 10 to 20. And
so it turns out that some of these galaxies, and maybe Tim's going to say the same thing, have detectable UV emission in the disks themselves. And we've done a series of studies, maybe, I don't know, Tim's been involved in some of these or not, but I've been involved in a handful of studies where we've actually looked at the UV properties of these galaxies, and we see star formation in these disks, but it's very low level. So, Tim, do you want to comment on
I
this?
just wanted to agree completely
Okay.
that there is some low-level star formation in these outer disks, it seems. You pick it up in the UV, also in the optical and very deep imaging, like the megacam stuff I was mentioning before. It's at a low level, and that probably reflects the fact that, you know, you're very low column density in the those outer parts, so your statistical density fluctuations that take you dense enough perhaps aren't as common. I mean, Andreas Schroeder did this stacking analysis looking at the H1 dominated regions of spiral galaxies and looking at where the CO sits, how much there is there. And I think it's more or less consistent with that, although some of the analysis still needs to be done. In the inner parts, I definitely think that in some 20% of early type galaxies, they are regrowing disks. They don't have to be very large disks. They can be 1-2 kiloparsecs even inside the bulge. This is changing the properties of the galaxies, so they're becoming more fast rotating with time. They're building kinematically decoupled components. They're building up the mass inside what you might call a bulge, but is actually a disk inside the bulge.
So can I return to this? Can I ask you a question about this, though? Because you said that of the 22% of early type galaxies in the Atlas 3D sample, which is somewhat special, that none of the galaxies with detected CO are slow rotators. So how do you turn a slow rotator into a fast rotator? All you're doing is you're speeding up fast rotators. Right? So do we never have slow rotators regrowing disks, ever?
I think there's several on that. So the first one is slow rotators tend to live in clusters where it's much harder to reaccrete gas. If they're not in clusters, they tend to be group centers in bright X-ray groups, so there's some suppression perhaps there of their gas accretion mechanisms. When I say there's none, there are a couple of galaxies that are technically slow rotators, but they're often ongoing mergers right now.
Okay.
So maybe you can have gas-rich merger and turn yourself back into a fast rotator. It's just whether or not this is happening in the majority, and I think it's probably not.
So I have a question about that. If you have rejuvenation and then quenching again, when you say it's a fast rotator, isn't that a light-weighted statement instead of a mass-weighted one?
Well, I mean, the mass fractions formed in these events are very low.
Okay.
So yes, it's a luminosity-weighted statement, but the luminosity doesn't contribute that much compared to all the old stars that are there. So.
I'm going to have to cut off the conversation here because I realize it's 10 minutes to 1, and I've been told by the organizers that I have to finish now. So we're not going to get to the modeling question. So I suggest that you argue about it over dinner. Sorry, discuss it gently over dinner this evening and on the trip this afternoon. Let's thank all of the speakers of this morning. It was very enjoyable.